So last lesson, just to sort of refresh your memory, and we're going to use the same example that we did last lesson. We talked about hypothesis tests, okay? And specifically relating to proportions, where a claim is made about the proportion of something, and we want to see if the claim is has convincing evidence to be true, or whether there's no convincing evidence that it's true. So we talked in general about how to do hypothesis tests. We used a simulation to help us sort of get a guideline or get a rough probability of what was usual, what was unusual. Now we're going to get a little bit more into the math and into the formulas of it. But like I said before, with confidence intervals, I showed you guys the long way to do it, and then I showed you the graphing calculator way. This first part is going to be the long way to do a hypothesis test, and you still need a graphing calculator to do it, okay? And the short way where you use a simple graphing calculator function, okay? So going back to this example, we're back to the NBA during COVID, okay, where they played in a bubble and teams played on a neutral court, no fans in the stands, yet the league randomly assigned each team to be a home team in 4 of its remaining 8 games to play. And then they gave us semblance of, this could be, no.
I think you're child. I have the US.
Okay. I need to close the door.
It is 1-1. 1-1, and then the last little thing. There wasn't 5 minutes left. Wait, we got 1 goal.
Okay, so we wanted to see, was there an actual home team advantage? Even though it was played in a bubble, yes, the league made it seem like with fans in the stands and virtual cheerleaders that there was a home team, okay, but was there really a home team advantage? So what actually happened, of the 88 games played, the home team won 49 times, away teams won 39 times. We want to know, is there convincing evidence of a real home team advantage? So to do that, we are going to remember, just to refresh your memory, when we did confidence intervals, we talked about a 1 sample set interval for a confidence interval. When we talk about a test, a hypothesis test, we are talking about a one sample Z test for a proportion. Okay? So just to kind of review what we did last class, is there convincing evidence that they had an advantage? What should you do when you see this phrase? You should conduct a hypothesis test. And the first part of a hypothesis test is stating your hypotheses. And remember, in the last lesson, we talked about the null hypothesis and the alternative hypothesis. The null was nothing's changed. So in this case, no home court advantage. The alternative was something's changed, or there was home court advantage. But we're not going to write it in terms of words. We're going to write it in terms of letters and numbers. Okay? So if there's no home court advantage, the proportion of games won by the home team should be what? 50%, but we're going to write it as a decimal 0.5. But we are trying to find convincing statistical evidence that there is a home court advantage. so that the proportions of wins for the home team would actually be greater than 0.50. So you need to state that, and you need to state what P is. And P represents the true proportion of games won by home teams. And so what we are basically testing, the question we are trying to answer, and we often use the phrase in a world where there's no home court advantage or home team advantage, where there is no home team advantage, what is the probability the home team won, home teams won, and remember what, they won 49 out of 88 games played. So what's the probability the home teams won 49 out of 88, or that's approximately 55.7% of the games. Okay. So is there an actual home team advantage, or did this just happen by chance alone? And how do we test that? Well, the way we did it in the last lesson is we ran a simulation. And we simulated 100 seasons, assuming that there was no home court advantage. Okay? So basically how this works is, like you would say, okay, you take 88 games, right? And you put in 44 H's. And you put in 44 A's. So 40, because if we're assuming that it's 50-50, we want 44 home team wins, 44 away team, and then we draw, okay? And then out of what you draw, you're not going to necessarily get 44 and 44. You may get 47 and 41, okay? So this is what happened when it was done, the simulation was done. Most of the time, the games won by the home team were around 50%. Sometimes it was significantly less, sometimes it was significantly more. The one that actually happened was the 56% one. So we want to know, what's the probability that this happens, 56%, in a simulation? Okay, so what's the p-value? Well, the p is the probability that the home team wins is 56% or more. Okay, so the p-value equals the probability of a win percent of 56% or more. In this case. Well, how many times did 56% or more happen? Well, 56 happened 4, 57 happened 3, 58 happened once, and so forth. So we go 4, 7, 8, 11, 12, 14 out of the 100 simulated seasons, or 14%. And so what does that represent? 14% chance home team won 56% or more. I know I'm repeating myself. Or more. We should make that look like an infinity symbol. Okay. Now, let's do the actual math with the sampling distribution. Okay. And with the formulas that we've used previously. So under certain conditions, we can assume that we have a normal distribution and that the mean of all the sample proportions will be, in this case, when we do a test, it'll be the null value. PO represents the null value. That's the original value that we put for P, which was 0.5. Right? We assumed it was 0.5. And then we're going to use that null value along with our sample size to calculate the standard error of the sampling distribution of sample proportions. So in our example, we have 0.5, and then using the formula, 0.5 times 1 minus 0.5 divided by the sample size, which was 88. So when we do this, we get approximately 0.053. And remember, we'll talk about the conditions we have to meet, because they're the same conditions we did before. So we've got the mean of the sampling distribution of the sample proportions. We've got the standard deviation or standard error. We know that it's normal, which means we can calculate the probability of getting 56% home team wins or greater. Well, first of all, we have to calculate how many standard deviations our observation, 56%, is away from 50% or 0.5. And how we do that is, if you remember, when we talked about Z values, we used this formula. This was way back in Unit 2, when we calculated Z scores. What does a Z score do? It tells us how many standard deviations above or below the mean we are, which is what we're asked to do here. So in this case, what we're doing is we're finding the Z value, which I will call, I'll just call it Z, by taking whatever the value we got, 0.56, because it was about 56% of the games. So that's P hat minus the mean, which is the null value, which is P0, over the standard deviation that we got. It's the same formula. And when we do that, we get 1.08. What does that mean? That means that the value we got, 56%, is only 1.08 standard deviations above what we expect it to be, the null hypothesis, which is not a lot, is it? Because remember, one standard, like when we start getting more extreme, we're talking 2 standard deviations, 3 standard deviations, more than that. That's getting extreme. Okay, but if we're within 1, we're fairly close to the middle, which tells you that it's not that unusual, but we still got to prove it mathematically. Okay? So just to explain this, our result, 56%, is only 1.08 standard deviations. I'll just put STD for standards. Standard deviations away from the mean, or in this case, away from the null value. This is not unusual. So really, right there, it kind of tells us that no, home teams didn't have an advantage, because that 56% is not an unusual result. But we need to be a little bit more precise than. So I've written this. This is what we did in Unit 2. Okay. This is what we're doing in this unit, a Z-test statistic. And that represents how many standard deviations a sample proportion is above or below the null hypothesis, or the null value. And like I said, and we calculated this, you will always get this. This is on your formula sheet. Okay, to find a standardized test statistic, when we do a test, hypothesis test, it's always the statistics we get minus whatever the null value is divided by the standard error or standard deviation. Okay. And the larger the test statistic, so the bigger that number is, the more, excuse me, unusual your measurements are. Because it tells us how many standard errors or standard deviations away. Okay? And the bigger, the more unusual it is. So using the normal curve and that 1.08 that we got, we want to find the p-value. Well, here's how you find it. Okay? How do we find a probability or an area using a normal distribution? Normal CDF. Because remember, this is what we're looking at. And this was 0.5. And we had 0.56. And I wanted to know What's the probability of getting that or higher? So I want to know this. So therefore, the lower value is going to be the number of standard deviations it was away. It's not going to be 0.56. It's going to be the number of standard deviations it was away. How many standard deviations was this away? It was away 1.08. So that's actually our lower value. Because we standardized it. And when we standardize it, the mean becomes 0 and all the standard deviations become 1. That's when we standardize scores. These are actually what we're working with, but because we standardized it, the mean now becomes 0. These notches all become 1 and -1, depending on what direction we go. So the lower, so I should have written lower, it's going to be 1.08. The upper is going to be a ridiculously high number. So let's just say 1,000 or 10,000. The mean is going to be 0, and the standard deviation is going to be 1. When you do all of that, you are going to get approximately 0.14 or 14%. What we got in our simulation. Okay? This would be the long way to do it. So what you would have to do is you would have to get your values here, your mean, your standard error. Then you would have to figure out your standardized test statistic. And then you would have to figure out the probability of getting your standardized test statistic or greater or less, depending on what the question asks. So that's quite a bit. Fortunately, there is one graphing calculator function that will do all of that for you. You don't have to do it. So let's look at that. And again, we're going to do the 4-step process: state, plan, do, conclude. So we're going to revisit this. This is how you should show your work. First thing, when we conduct, remember we're doing a hypothesis test. Under the state, this is where you state your hypotheses using numbers and symbols. So we already did that previously. No home court advantage means the true proportion will be 50-50, 50% or 0.5. If there is a home court advantage, it will be greater than 0.5, where P equals true proportion of home team wins. That's the state part for a hypothesis test. The plan. This is where you state, what am I going to do? And what are the conditions that allow me to do it? So the plan part. What are we going to do? We will conduct, we don't create. Remember, confidence intervals we create, hypothesis tests we conduct. A one sample z-test. Or P. If and then you have to state your conditions. What was the first condition? Do you remember?
Randomness.
Random. Well, what does the question say? I believe it said random nearly. Yes, the league randomly assigned each team to be the home team and away team. Okay, so home and away were randomly assigned. Now, this is a little different. In a way, what's that?
Oh, it's-
Okay, thank you. That's okay. I don't know. We are doing an experiment in a way, because aren't we randomly assigning groups to home and away? Okay. When you conduct an experiment, you don't have to do the 10% condition. Okay? Not necessary, because what we've done is an experiment. So and when we do experiments, it assumes independence. So that's why we don't have to test it. And then the last one is the large counts. And those are the ones that are greater than or equal to 10. So what do we have to calculate? We have to calculate the sample size times the null value, and the sample size times 1 minus the null value. Just like when we did confidence intervals, we did n times the sample proportion, n times 1 minus the sample proportion. But we don't have a sample proportion. We have a null value that we're working with. So this is 88. And remember, null value is 0.5, so that's 44. 1 minus 0.5 is also 0.5. So it's also going to give us 44. That's good. Both of those are greater than or equal to 10. Check, check, check. That means we can proceed. Now, instead of doing all that work that we just did, you use your graphing calculator and you use this function. So to do this, you need to go to stat and then scroll across to tests. And you need to find where it says 1 prop Z test. Be careful. Don't confuse it with 2 prop Z test. Don't confuse it with 2 sample Z test. Those are different tests we're going to do later on. So it's number 5, 1 prop Z test. And you're going to be asked for the following. Okay, so we are going to do a 1 prop Z test. This is the do phase. What's the no? Lost?
Yeah.
Oh.
2 wells, yeah, it's wells. Usually it's so serious. There's no how to believe.
No. So the null proportion was 0.5. What does X represent? X represent, and you can write it across, you don't have to write it down. X represents the number of wins for the home teams. Okay, and what were the number of wins?
49.
49. Out of the sample size of 88, which is M. And then finally, is our alternative hypothesis greater than P0, less than P0, or different from P0? Greater than. So we want to do this one. And when you punch all that in,
Color doesn't matter, right?
sorry,
Color doesn't matter.
no, color doesn't matter. That's if you wanted to graph it. Sorry, I got 49, 88, we are greater than, we want to calculate. And the one, like, first of all, that Z, that tells you how many standard deviations away. Notice that that works out to 1.07. We got 1.08. That's because of rounding, it's slightly different. We want that P value. We want that P value, which is approximately 0.14 or 0.143. Because that tells us the probability of the home team winning 56% of the games or more, which we saw when we did it the long way was also 14%. Okay, so we can make our conclusion. So we conclude by saying, because our p-value is greater than, and if you notice at the beginning of the question, I should have pointed this out, it will tell you the significance level that you have to meet. Okay, in this case, it's 5%. A lot of times it'll be 5. Sometimes it might be different, but most of the times it'll be 5. So because our p-value is greater than alpha of 0.05, and remember this was 0.143, we reject HO. And then you have to follow this up. We do not have convincing evidence. There was home team advantage. That's a completed solution. Okay, with the 4 steps for a hypothesis test for one proportion. Now, you may have noticed when you did your graphing calculator, you saw greater than, less than, and you also saw not equal to. When do we use not equal to? Well, it's called a two-way test or a two-sided test. Okay, that means you're testing an alternative in both directions. And what would that mean? Let's go back to our example. Instead of saying, would the home teams have an advantage, we would ask, is there convincing statistical evidence that either home or away had an advantage? So because of this, I'm going to use not equal. So when I do my state, I've got HO, no home team advantage, the proportion is 50% or 0.5. What I'm trying to prove is, was there a home team advantage, or was there a home or away team advantage? Either way. And if it's either way, it could be less, it could be more, which means it's not 0.5. It's either above or below. I can't use greater than or less than. I just use not equal. And then, of course, I would write P equals, and then I'm not going to rewrite all this stuff. It's the same thing as before. The plan is the same as before. We will conduct a one sample Z test for P if, I'm not going to rewrite these conditions because we've already proven that these conditions were met. Conditions were met. We already did that last. The do is going to be a little different because we're going to go one prop Z test. The null value is still 0.5. The X value is still 49. The sample size is still 48. But this time, we are using not equal to. And when you use, not equal to P0. When you do that, you get a p-value even higher, actually double what we got before.
B-O,
Sorry, actually, that says equals.
okay.
I just changed it from the colon. So again, for our conclude, and I'll just keep it shorter, because p-value greater than alpha, we again reject HO. And then we would say we don't have, and then we would have rewrite the same sentence that we did before. We don't have convincing evidence. Okay. Just remember, because you're gonna hit them when this is below alpha. What are we saying? We fail to reject HO. We don't say we don't reject HO, we fail to reject HO. We have convincing evidence of whatever the alternative hypothesis was. Okay.